We'll start at 7. Let me know if the audio is okay. Yeah, so we're still in the Whittaker and Watson series at the moment. My plan is to finish the first chapter and then switch to the other analysis book called Advanced Calculus by Loomis and Sternberg. So actually, I quite look forward to the Advanced Calculus because the chapter 1 over there serves as a good introduction to proof writing. I mean, not really an introduction, but more or less a recap on the basics of proof writing, as well as the notations, the logic in modern abstract mathematics. So hopefully, I don't think I will, because I can't stay for too long today, because last time I streamed for 3 hours. I hope I will be able to do over 2.5 hours today. And then hopefully discuss the rest of the Dedekind's cut. Perhaps that's even a little bit more ambitious. The thing about Dedekind's cut is that there are so many details to check. But once again, we just wanted to do this once and then never use this construction again, because after we know there is a set called the real numbers, and we can simply work with its properties and forget about the underlying constructions. But at this point, we have to do it at least once. This is, in my opinion, a proper start of analysis. So basically, we convince ourselves that there is such a set called the real numbers to work with, and then we can build upon it. This is so fundamental. All right, so without further ado, let's get started. So I think just to briefly remind the new viewers, I do post stream summary videos after each stream. Let's be honest, each stream is quite long, and there's going to be at moments where I struggled, and which is not a bad thing, I mean, per se, but in the summary I will summarize the activity, obviously, what do we go through, and where do we find difficult, where do we find easy, and why do I find certain things more difficult. Okay, so each reflection or summary video will be roughly just about 10 minutes. If you're interested in the details, you can always go back to the stream itself, the stream recording itself. So that's the idea. All right, so let's get, without further ado, getting back to the Dedekind's cut. Okay, so the Dedekind's cut, we finished the addition, all the addition properties. So we have 5 properties for the addition which we wish to satisfy. There are closure, commutativity, associativity, existence of additive inverse, aka 0, and the existence of additive inverse, aka for every x there is a minus x. These are all verified. Okay, so now we wish to do the same for multiplications. So here there's only one sentence in the maybe two in main text. It says the product of 2 positive real numbers which are understood as cuts, okay, alpha and beta, is defined by the R class. The R class stands for the collection of reals that are sorry, not the collection of reals, the collection of rationals that are to the right half section of the rational line, basically, the R class. We don't deal with R class in our construction, but this is what it is. Alpha and beta is defined by the R class A2, B2, and the L class of all the other rational numbers. So this says that if we pick two cuts, right? So each cut comes with two classes. Each has a left class and a right class. And then, by the way, these are also positive. Actually, this is a major bothersome point about multiplication, because you have to define multiplication separately depending on the sign. When it comes to addition, we don't need to separate the cases. So first we have to define the product of two positive cuts, and then define the product between cuts having opposite signs, basically. So that's just one line here. What we need to do is to first recast this definition into our terms, okay, and then verify the properties of the multiplications for cuts, basically. All right. So let me actually I will open up my note. Hang on. You can see on the screen, this was the notes from the last stream, but the file is getting a bit too large, and in which case Word is getting slower and slower. So I will start a new note today. But there's still a few things we need from this note. So this is our definition of a cut. We definitely need that. Okay, so let me just start a new document and put whatever I need into this new document. So I need the definition of cut and the two properties that comes in handy. Okay. So I need these things, and let me just copy it here. So I need the definition of a cut, and the proofs of these two propositions are not essential, but I need the definition of cut for sure, and I need a definition for the multiplication. So let's start by defining multiplications between positive cuts. All right, so that's the first thing we do, just like in Whittaker and Watson. Definition. Okay. So this is multiplication between two positive cuts. Okay. So we denote. Actually, let me start by writing the notation first. Denote the R plus. Okay. Denote R plus the set of all positive cuts. Okay, and by that we mean the set of all positive cuts. Let's write alpha such that alpha is a cut. Alpha is in the big R is the set of all cuts. Okay, and alpha in R such that alpha is greater than 0, and we specifically discussed what this means. Okay, this is an order relation between two cuts, alpha greater than 0. Okay, and that means 0 is a proper subset. The cut for 0, okay, is a proper subset for the cut of alpha. This is what it means. Okay, so now we have the set of all positive cuts, and now we define cuts on this. We now define multiplication on this set. Okay. So if definition, if alpha and beta, alpha in R plus and beta in R plus, so these are two positive Dedekind cuts. Okay, and how do we define their multiplication? We define the set alpha times beta. So this is a new cut. Okay. Of course, we need to verify this is a new cut. But first, the definition is rather straightforward. This is the set of all rational numbers p. Okay. The set of all rational numbers p such that p is less than or equal to r times s where R comes from alpha and S comes from beta, and R and S are both positive. So that's the definition of the multiplication. Okay, so let me finish this. So R for some, or should we say there exists, P such that there exists. That's right, there exists. R comes from alpha. Okay, and that's the first quantifier. The second quantifier is there exists. S comes from beta, such that P is less than or equal to R times S. Okay, and we also want to make sure that R is greater than 0. R and S are greater than 0. Okay, so let's write R and S greater than 0. So that's it. So that's the definition of a multiplication. Okay, so let me just draw the picture real quick. It's always nice to draw a lot of line segment plots in the study of the Dedekind's cut. All right, so let me see. Let me just show it right here. So this is alpha. Okay, so this is alpha, and now we have another cut, say beta. Okay, so how do we define multiplication of those two? Okay, by the way, this stands for 0, by the way, just to show that alpha is and beta are both positive. Okay, so this is alpha times beta. Okay, for an arbitrary P in alpha times beta, P is less than or equal to sum R times S. This is R and this is S. P is less than or equal to the product of R and S. Okay, and R and S are both positive. So that's the definition of the product between two positive cuts. Okay, so this is our definition, and what we want it to satisfy. We need to verify it behaves the way we want to, right? So for that, let's go back to our note on the last stream, which is March the 31st. Okay, we didn't finish defining the field. All right, so in the field, we need to have two operations, addition and multiplications. Okay, and they need to satisfy a bunch of axioms. We only defined the axioms for addition last time because we only managed to complete discussing addition last time. So now let's complete this definition. By a field, we mean a set F equipped with two operations, addition and multiplication, which satisfy the following properties known as the field axioms. And they're grouped as A, M, and D. Last time we only have A, axioms for addition. So now let's start with, let's keep writing the axioms for multiplication. Okay. So what are the axioms of multiplication? Well, pretty much the same thing. Right? We still want closure, of course. We want the two, we want the result of the multiplication to be still in the set F, okay, the field. So we want that to happen. So that's right. Let's just copy this down, and actually, you know what? This is M. This is M. Okay, M1 is the multiplication axiom that says closure. Okay, if X is in F and Y is in F, then X times Y, okay, which we simply write X and Y, XY. Okay. So let's we often abbreviate X times Y as simply XY, just like in elementary, algebra. All right. So this is the first property we want closure. So we need to show that the multiplication we just defined is still a cut. Okay. M2. Let's say if we want the multiplication to be commutative, right? So this is a direct analog of A2 for all X and Y in F. x times y equals to y times x, commutativity. All right. So, and then let's do associativity. Associativity also holds for multiplication. So that's the axiom, x times y and then times z is equal to x times y times z quantity. Right? That's the associativity. We want that as well. Actually, it's M3. Okay, so A4 needs to be modified to the existence of the multiplicative identity. So what is a multiplicative identity? Well, that's just 1. Everything, if anything gets multiplied by 1, becomes itself, right? And so basically that's the definition of 1. F contains an element denoted as 1. That is, and such that 1 is not equal to 0. 1 is not equal to 0. This is a abstract definition, so there's no a priori reason that these two should be distinct objects, right? So therefore we add this particular requirement that 1 is not equal to 0. So the additive identity and the multiplicative identities are distinct. That's in the axiom. Okay, now we want for all x in f, and for all x in f, x times 1 is 1. Okay, or 1 times x is x equals to x. This is the multiplicative identity. All right, so that's M4. M5, what's M5? Well, M5 says if you have x in f that is non-zero, then there exists a multiplicative inverse, basically the existence of reciprocal. So we want that as well. If x, for every x in f such that x is non-zero, okay, there exists an element denoted as not as minus x, but rather 1 over x, such that x times 1 over x is equal to 1. And that's the multiplicative inverse. So this is what we want. X times 1 over x is equal to 1. This is the multiplicative inverse. All right. So these are the 5 axioms for multiplication. But now that we have both addition and multiplication, we still need one more property. That's the distributivity. We want the distributivity to hold. So that's just the single axiom, or the distributive law. Okay, the distributive law. We want that. It says for all x and y and z in f, okay, x times y plus z is equal to x times y plus x times z. For all x, y, z in f, okay, x times y plus z is equal to x times y plus x times z. Right. So these are the usual properties of addition and multiplication which we want to hold. Right. So that's the definition of a field. And by the way, combined with our previous notes. Okay, so this was our previous note, which we defined order relationship earlier. Okay, so this is the definition of an order. A set with an order is called an ordered set. And now we also have the field axioms in our new notes. We want these attributes of the set F to be compatible. Right? So it's not just required that an ordered field is an ordered set and a field separately. We also want these structures to interact. Right? So basically, we want the order relationship and the arithmetic operations to work in the way we expected. Right? So that means we need some extra requirement as well. So for example, if you have an inequality, so to say, if you already have an order relationship, let's say x is less than y, and you just add two identical elements to each side, right? then the inequality direction should be preserved. Right? That's the usual property we expect from an inequality. So for that, we need to add these axioms as well. So these are also something we want, a definition. Okay, so we now define an ordered set and a field, and now we need to define an ordered field. Okay, an ordered field is a field, okay, which we just defined, is a field which is also an ordered set with the additional properties below. All right. So we need the first property, which is x plus y less than x plus z. If x, y, and z are in F and y is less than z. Okay, so that's a completely natural property to hold, right? So we want the essentially we want the order relationship to be compatible with the arithmetic, and also something similar for the multiplication. X times y is greater than 0 if x and y are in F and x and y are both greater than 0. So we want that. So that's an ordered field. Okay, so we started from defining an ordered set and then proved, what's it called? Proved the least upper bound property. That's the first major achievement for the construction Dedekind's cut. Right? Because the least upper bound property is what distinguishes the real and the rational. But still, after that breakthrough, we still need to verify what we had earlier in the set of rationals are still hold. Right? So the field property and the ordered field property are both true in the set of rationals. We just now need to see everything is still safe, okay, by extending the rationals to the real. Okay, so that's the ordered field. So now our objective is to prove M1 to M5, D, and these two properties. If we can do that, then the real number is constructed. Okay, so that's the plan. Okay, so how do we proceed? Okay, we just define the multiplications between two positive cuts. Okay, so let's get on with proving M1. Okay. Okay, so M1 is the closure property, which we just stated. So we need this proposition. Okay, basically, I'm just going to copy down these multiplication axioms, and I'm going to create propositions based on them. Okay, the proposition 1 says, okay, if alpha is in the set R plus. Actually, we want R to be a field, right? We want R to be a field. But here we only define multiplication in R plus. So actually, why don't we just prove something stronger? Like to prove that this multiplication is closed in R plus. Okay. Alpha is in R plus and beta is in R plus. Okay, so we need to show alpha times beta is in R plus. Okay. i.e. we need to show it is a cut and it is a positive cut. So that's the first proposition. This verifies M1. Okay, and then let's do the second proposition. So we don't that's commutativity. So they just convert that sentence to for all alpha and beta in the set R plus. Okay, then you have alpha times beta equals to beta times alpha. And based on our experience from last time, proving commutativity and associativity should be quite easy, because it just boils down to the commutativity and associativity for addition and multiplications between the rationals. So it should not be too hard. Okay? But anything can happen. We have to actually prove it to appreciate what is really going on. Okay. Because unexpected difficulties can always arise. So alpha times beta then times gamma is equal to alpha times beta times gamma quantity. That's this proposition. That's the associativity proposition. Okay. The next proposition. It says R plus contains an element denoted as 1. I mean, if it's in R plus, then it has to be in R. Right? Such that 1 is not equal to 0. Actually, let's prove something stronger. Let's prove that 1 is greater than 0. If you can prove 1 is greater than 0, then it's already not 0. Right? Remember, that follows from the axioms of order. Exactly one of three relations is true between any two elements in an ordered set, x and y. Either x is equal to y, or x is greater than y, or x is less than y. Right? So if you can prove x is greater than 0, that means x cannot be equal to 0. And for all x in R plus, actually, let's use alpha just to be consistent. Use Greek letters. By the way, we always use Greek letters to denote cuts, and always use Latin letters to denote Latin letters that start from P, Q, R, S, and so on to denote the rationals. Okay, so that's the next proposition. The final proposition. By the way, I should write this verifies M2, this verifies M3, and this verifies M4. Okay, and last proposition says for every alpha in R plus, let's just say, such that alpha is non-zero, there exists an element denote as 1 over alpha. We need to find the reciprocal cut such that alpha times 1 over alpha is equal to 1. Right? So that's the list of objectives just for verifying M1 to M5. So I suspect we're going to borrow heavily from the proofs for verifying A1 to A5 because it's quite natural. So, but we still need to make sure that the argument stands on their own. Okay, so that's our objective. So let's go back to the notes for the last stream. Here we defined addition. Okay, the first proposition, the closure. So for closure, we need to verify the three defining properties of closure. sorry, not closures, 3 defining properties of cuts. Okay, so we need the result of the arithmetic to be not empty and not the whole of Q. And we also need to have this property basically says if a point is in the cut, okay, if a point is in the cut, then everything to its left is also in that cut. That's the second property. The third property says no cut has an absolute, no cut has a maximum element. In our cuts, we only work with the left class, so that's why we discuss maximum only. So, all right. So basically, let's put these facts together. Not facts, but rather objective bullet points together. Okay. Let alpha and beta to be in R plus. Okay. Okay. So, and then we need to show alpha times beta is also a cut, which is actually a positive cut. So why don't we just show that it is a cut and then discuss positivity. Okay, sorry, I'm a little bit tired today. Let me just have a little sip of coffee. Okay, much better. Okay, first one. Feel free to say hi, by the way. Hello from Waterloo, Ontario. Wow. Are you stalking me? Hi there. Which area? I graduated from Waterloo, by the way. Okay. So are you a student? Shah? I'm just wondering. Anyway, hi from Waterloo as well, actually. We're in the same city. My goodness, what a small world. Okay. So the first property says yes, I am. Okay, great. Okay. Well, good luck with your study. You must have exams right now. No, it's the exam season. You're watching my live stream. Thank you so much. Thank you so much. Hi from Hong Kong. From the UK, from the UK, not from Hong Kong. Okay, I'm sorry, from the UK. John Fletcher, I remember you. Yeah, a great job, by the way. You're working on the Dedekind's original book, right? If I'm correct. So yeah, I watch your videos from time to time. So, and now we're just trying to recast everything into modern notations. So here we have this property that needs to be verified. Alpha times beta is not the empty set, and or the whole of rationals. Okay, so we need to do this proof first. So how do we manage to prove that the sum is not empty or the rationals? Right. So should be helpful. Let's see if anything we've done earlier can be imported, so to say. Okay, we wrote, since alpha and beta are cuts, they're not empty. Okay, fair enough. And thus, so alpha times beta. Well, we have proved by contrapositive. So that's actually not a bad idea. So because we if you want to prove by contrapositive, okay, we want to this is a negation statement. So if you want to prove, okay, contrapositive proofs works like this. So let's say if you have two propositions, okay, P and Q, and you want to prove P implies Q, right? We can instead prove not Q implies not P. Right? So that's the contrapositive proof. Prove that if AB is not real, show that A is not real or B is not real. Yeah, so that's what I'm trying to get to. That certainly a good idea. So if let's say A is alpha times beta is empty set. Okay, so let's do your idea. If alpha times beta is the empty set, that means what? That means there is no such P that satisfies this property. Right. So let's start by assume for a contrapositive argument, in case we forget later what we're doing. All right. So for a contrapositive argument, and okay, and so this means there is no P that satisfies this property. Alpha, there's something from alpha called it's exam season for us now. I'm in my lab's office catching up on some research. Wow, grad student. Fellow grad student. I mean, I was a grad student. I'm no longer. I graduated. But yeah, good luck to your work, man. So now we have this assumption that alpha times beta is that A equals to C plus DI, where D is not equal to 0. DI? What do you mean by DI? Or we're not dealing with complex number? No? AB equals to assume alpha times beta is an empty set. So there does not exist such P. Under second year undergraduate, wow. And you're doing research work at second year. Very commendable. Good job, man. I think a direct proof is actually maybe easier. So we can just enumerate an element, right? We can just enumerate an element. So because alpha and beta are positive, okay. So actually, I'm sorry, I don't want to delete this for now, okay, just in case I need to come back to it. But basically, since alpha and beta are positive, right, alpha and beta are positive, there exists a positive rational in it, right? There exists R in alpha and beta, and S is in beta. If it's not real, then it is complex. Actually, you know what? We're not even considering complex numbers yet. Okay, so we're in this state of constructing the rationals to the real. So this is so as far as our progress is concerned, the real numbers does not even exist at this moment until we verify everything. Towles and Allison had a really good explanation of Dedekind's cut, which also spent a long time building proofs axiom of real numbers, starting from page 1. Yeah, I know, like Terence Towle, right? Sorry, didn't see the real plots. Okay, no worries. So here we have alpha and beta, both positive. There exists R and S in these two sets with alpha and with R and S, both positive. Both positive, not equal. Okay. So we can just pick P equals to 0 then. You can just pick P equals to 0. Zeros then satisfy this property. So that's done. Thus, the rational number 0 in Q. Okay. So the rational number 0 satisfy this property. Right? Okay, so that means that this is not empty, so we're done. Okay, so we don't need I mean, I'm not saying it cannot be done, right? So this is already enough for proving alpha times beta is not empty. Okay. Okay, so now we need to prove that it is not the whole Q. How do we prove that it's not the whole Q? Well, we need to construct an element that is not in the product set. Okay, we need to construct an element that is not in the product set. For that, we use the property of the Dedekind's cut that alpha and beta are not the whole reals. Okay, alpha and beta are not the whole reals. So since alpha and beta are cuts, okay, there exists. I can use the letter P. I can use the letter P and Q. P not in A, not in A, not in alpha, and Q not in beta. And they both have to be positive, obviously, because alpha and beta are positive cuts. Thus, P and Q are both positive. P and Q are both positive, and the product between P and Q is not in the set alpha times beta, because this is greater than 0, and in fact greater than P is greater than everything that is in alpha, and Q is greater than everything is in beta. Okay, so thus you say P is greater than all A for all A in alpha, and Q is greater than B for all B in beta. Okay, so thus P times Q is greater than all, let's say, S for all S in the set alpha times beta. Okay, all right, so that tells us basically the PQ is not in alpha times beta, and therefore PQ is not in the set alpha times beta, so therefore alpha times beta is not the whole Q. Okay, so we're done here. We're done with the first property. The next property we need to show that if, let's say, if P is in alpha times beta, then everything to the left of P is in alpha times beta as well. Then if P is in alpha times beta and Q is less than P, then Q is in the set alpha times beta. So that's what we wanted. Okay. All right. So so first of all, if it's obvious that if Q is less than or equal to 0, then it's obviously in alpha times beta, right? Because we already said that 0 is in alpha times beta. I didn't write that. I mean, when I wrote this, I meant to check that 0 is in alpha times beta. Okay. All right. Okay. So here, if Q is negative, or sorry, if Q is less than or equal to 0, then Q is automatically in alpha times beta. Okay, so we're going to assume Q is greater than 0. Okay, so assume Q is greater than 0. Okay, so now let's see, how is 0 in A times B? Okay, because A and B are assumed to be positive cuts. So in this diagram here, we said because A and alpha and beta are both positive. Okay, so you can pick an arbitrary positive RNS. The product must be greater than 0. So therefore 0 is in the product cut. Okay, great. So yeah, great question. So now let's see what happens if we have Q greater than 0. Q is greater than 0. Oh well, you can just use the same same element R and S that comes from the set alpha and beta, whose product bounds P, and use that to bound Q, right? So this is, again, very trivial. Assume Q is greater than 0. Okay, if P is in alpha times beta, then by the definition, P is less than or equal to R times S, for some R in alpha, and S in beta. Okay, so this is basically the property of P, and therefore, since Q is less than P, we have for the same R and S. Okay, Q is less than P. Q is less than R times S. Q is less than R times S, and therefore satisfy the property, and thus Q is in alpha times beta. Again, very easy. Okay, so next up, we need to show that the set alpha times beta has no greatest element. Right? So that's property 3. So actually, how do we phrase that last time? We phrase it as such. If P is in the result of the arithmetic, here we use multiplication instead of addition, and you have Q with Q less than P, with Q, no, this was the previous property. Sorry, I meant the last one. This one, okay. If P is in alpha times beta, then there exists something else in alpha times beta such that P is less than R. This says the Dedekind's cut has no greatest element. So we need to show that. Well, to do so, we would have to construct another element R. This is trickier. Right? This is trickier. So how do we do that? Well, we have to make use of the fact that alpha and beta has no greatest element. Right? So alpha has no greatest element, so there is something that is greater than R and something that is greater than S, and their product must be greater than R times S, basically. So how do we, based on that fact, and construct an R? So we will have to do some scratch work, basically. So let's say you have an R plus delta R. Let R be the maximum. Maximum alpha and beta. Maximum AB, what do you mean by? The thing is, alpha and beta, they have no max element. We do not allow cuts to have, you see, I draw this open interval sign here. I cannot, that's in the definition, by the way. This is in the definition. No cut can have a greatest element. So you can only like approach the boundary, so to say. Okay. Basically, that's the objective. Okay. So we have R plus delta R, which is still in here. Okay. And then you have S plus delta S, which is still in beta. And their product obviously is greater than R times S. So R times S is greater is greater than P, right? R times S is greater than P. So we need to construct something. Are the letters in conflict? The letters in conflict. So let me use a different letter, say U. Okay, U. Okay, I need to construct this U. U is an alpha times beta. How do we do that? Well, so can I maybe these two, when multiplied together, you get R times S plus R delta S plus S delta R, and then plus the second order term ds dr. Okay. So we just pick this to be our U. U is less than the product of these two because I ignore the second order term if I borrow the calculus heuristics. Okay, so that's the idea. Okay, so basically we can construct U as such. Okay, so since alpha and beta are cut, since alpha and beta are cut, they're actually, let me first use the assumption that P is in alpha. Since P is in alpha times beta, P is less than or equal to R times S for some, actually, I can copy this, and I forgot to write, actually, with R and S both positive. Okay. Lots of details here. And actually, I think I will put up a GitHub page to basically collect all these notes, so you can look through them and at any time you want. Don't have to go to the stream recording to find what I wrote. Okay. I think that will be helpful. Okay, so that's the assumption P in alpha and beta. Since alpha and beta are cuts, there exists. I'll just use the same notation as I did in the scratch work. Delta R in alpha, which is greater than R. And S plus delta S in beta with delta R and delta R, delta S positive. Okay. So now let our U to be R times S plus R delta S times plus S times delta R. That's it. That's our U. Okay, so clearly U is greater than P. U is greater than P. Right? That's what we wanted. Or right, P is less than Q. Okay. P is less than U. P is less than U, and U is also in alpha times beta. That's the next requirement. We want U to be less than alpha times beta. Indeed, the U here this is less than the three terms plus the so-called second order term. Okay, so that's R plus, can't you claim that for all P in AB there exists R can you claim that for all P in AB there exists R in A and S in B such that hang on, what is this for? I can't claim that, but what does that accomplish? Because I wanted to show these three properties, right? I'm working on a cert. I assume that P is in alpha times beta. I want to have an element that is greater than P and is still in the same set. What does that claim do? Okay, I'll think about it later, okay? There you go. We have delta R and then times S plus delta R, delta S, right? So this, because these two are still in the same cuts we picked earlier, right? R plus delta R is in alpha, S plus delta S is in beta. So U satisfies the property of alpha times beta. U is in here. U is less than something that comes from alpha times something comes from beta. Right? So that shows U is in alpha times beta. Therefore, if all P greater than 0, and that's all. If all P greater than 0, there exists no R in A and no S in B such that R is less than 0. That solves the problem. Thanks for the idea. Okay, so what we're trying to do here, once again, is to show that alpha times beta has no greatest element, right? So you pick an arbitrary element in there, and you show that there's something bigger than that. I'm not sure if this is connected to our goal. That makes sense. Okay. I think what you've written is true. That's the thing. I think what you've written is true, but I don't know why this is relevant to our three goals here, right? So that's the thing. I'm pretty sure these aren't the unique steps. Okay, I'm not saying this is the proof. I'm pretty sure there's other ways to construct the U, for example. But for existence proof, you will have to give an example of it, right? That's the requirement there. So here we let P to be an arbitrary element in alpha and beta, and so by the definition alpha times beta, there exists R and S, such that R times S bounds P. And we based on R and S, we construct R plus delta in alpha and S plus delta in beta, because alpha and beta has no greatest element. You can always squeeze a little bit to the right, right? It never reaches the maximum, because the maximum doesn't exist. Right? It shows R plus, A is in R plus and B is in, show A is in R plus and B is in R plus. Actually, we assumed A is in R plus and B is in R plus, so that's the premise. Right? That's the premise. Okay. Oh, actually, you said you wanted to show that alpha times beta is in R plus, right? That's a positive cut. That's a positive cut. Here we only did that alpha times beta is a cut. But we can easily upgrade that. We can easily upgrade that to alpha and beta is in R plus, because here we already show that 0 is in the alpha EI by contrapositive. So if we already have 0 is in the cut, there has to be something greater than 0 is also in the cut, right? Because the cut has no greatest element. 0 is in the cut, so there's something positive in the cut. It has to be a positive cut. Right? So there's no extra work needed. If you prove that 0 is in the cut, then it's already a positive cut. Because the zero cut, right? The cut for 0 has no greatest element either. So the cut 0. Okay, imagine if you plot this round bracket right at 0. 0 cannot be in the set. So if 0 is in the cut, this must mean alpha times beta is a positive cut. Right. All right. So I think we're done here, okay? I think we're done with proving the closure property, okay? Which is not that hard, but we spend a little bit more time than we probably needed, okay? But it's a good practice anyway, because it's been a week since I touched this stuff. I remember when I first learned this stuff, and by the way, my course, just for personal experience, my course on analysis when I took as an undergrad, totally just hand wave over this, okay? And actually, with full respect, sort of like how Whittaker and Watson did, and just say, okay, this is how it's done, and the rest is left as exercise. I spent a whole day, I remember, I spent a whole cold Canadian winter day. It was snowing outside, I had nothing better to do, so I just stayed home and proved Dedekind's cut satisfied the real axioms. So that was how I learned this stuff, and it was 10 years ago. So anyway, right, and now let's do M2. Okay, M2 and M3 should be very easy, okay, if nothing surprises us. These two should be very easy. Okay, let's go. Proof. By the way, here, the two sets being equal is understood in the same meaning as set equality. Okay, if two sets are the same, that means they are subsets of each other. Okay, so this is what we mean. And let's do that instead. Okay, let's do the two containment. This should be very easy if I'm not mistaken. All right, so let's do the first direction. Alpha times beta is a subset of beta times alpha. And by the way, I write subset this way without the little dash at the bottom to indicate just pure containment. Okay, it does not mean proper containment. Something always causes confusion here. So basically, so to do that, we use a classic element chasing argument. Let P to be in alpha times beta. Okay, alpha times beta. So therefore, we can just copy this property. We used a bunch of times. Then P is less than or equal to R times S for some R in alpha and S in beta, with R and S greater than 0. All right, so, well, you can just swap the positions of these two elements. So, thus, this is completely trivial. So, thus, P less than or equal to S times R for some S in beta for the same, actually, for the same S times R. For the same S in beta and R in alpha. Okay, with S and R greater than 0. So therefore, P is in the set beta times alpha. P is in the set beta times alpha, so we're done. This proves that. This proves one containment, the classic element chasing proof for set containment. Okay, not terribly exciting. The other direction is similar. Okay, so that's it. What's going on? So that's this proposition done. Okay. Once again, it boils down to the fact that multiplication between rationals is commutative, right? So not much to say there. Okay, so the third property, associativity, is once again done by element chasing. So let's do the first containment. Actually, yeah, it's my subset notation. So you let P to be in the first set, alpha times beta quantity times gamma. Okay. So that's what we mean. Okay, so how do we unpack that? Well, then there exists blah 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 r times s, where r comes from alpha times beta, and s comes from gamma. Right? Now with r and s positive. Okay, since since r comes from alpha times beta, you can unpack this even further. R comes from alpha times beta. There exists, or should we say, r is less than or equal to what? What letters are still left? Okay, u times v for some u in alpha and v in beta, with u and v positive. Okay, so then this shows that p is less than or equal to, because r is less than or equal to u times v, right? So p is less than or equal to u times v times s. Okay, and so, well, so that means, well, this is u times s. Well, u times s comes from beta times gamma. Since v times s comes from beta times gamma, we're done. Right? P is less than or equal to something that comes from alpha, which is, just let's write it this way, okay? Just that's the associativity part, the associativity of the rationals, rational multiplication. So since we're done. Actually, let's not write that. Let's just write P is in the set alpha times beta times gamma. Okay. Okay, so that's it. Right. So this proves the forward containment. This proves the forward containment. The other direction is entirely similar. Okay. Actually, be very careful when we write this sentence. Sometimes you think it's similar, it's actually not. Okay. Be absolutely sure when you can write this. No. Okay. Because here it actually is completely similar. Anyway, so let's go to the next proposition. The existence of 1. Well, how do we define 1? Right? It's the existence of 1, right? So we need to enumerate a cut and call that 1, and then verify it actually works. Right? 1 is greater than 0, and also 1 times alpha is equal to 1. Is equal to not 1, equals to alpha. Okay, so proof. Well, for this question, we're going to actually denote 1 with a subscript r, because I don't want to confuse the 1 as a rational number and 1 as a cut. Okay. In the end, of course, we will erase such distinction. Okay. In the end, there will erase such distinction, because once the existence of a complete ordered field is proved, you can prove that there is a what we say an isomorphism between cuts that are defined by rational numbers and the actual rational numbers. So in that sense, this identification allows us to say Q is a subset of R. Okay, but that's after everything is shown. So here we just wanted to construct this element 1R, okay? And so it is quite obvious what this should be. Let's just define 1R to be the collection of all rationals that is less than 1. Okay, so this is the set of rationals. P is in Q such that P is less than 1. P is less than 1. So this 1 here, bare 1, refers to the rational number 1. Right? So we cannot write intervals yet because interval stands for real numbers. We don't actually have real numbers yet. Okay, so basically it's the same idea as the open interval minus infinity to 1, but with all the rationals in it. All right, so this is our cut. This is our candidate cut for 1. Okay, we now need to prove that 0 is less than 1. And this is obvious because every element in 0 is less than 0 and is automatically less than 1. So that's completely trivial. So immediately, that's right. We have, but even though it is trivial, it's a good practice to think about order relations. Immediately we have 1 is greater than 0. Because this less than symbol or greater than symbol between cuts denotes proper containment. So first of all, 0 is in 1. Actually, let's write that. If what's 0R, by the way? 0R, it was something we defined earlier in the last live stream. We're doing A4. The existence of 0 for addition. And 0 is defined as the set of rationals that is less than 0. Right? So this is our definition of 0. Recall. This is our 0 cut. Right? Immediately we have 1 is greater than 0. If, let's say, S is in 0, that means S is less than 0, and therefore S is less than 1. The usual order relation between the rationals works. Okay, and thus S is in 1. So this shows containment. And now we need to show proper containment. Why proper? Well, 0, the number 0, okay, the rational number 0 is in 1 but is not in 0R. It's proper containment. And this proves containment only. Actually, let me continue. Also, 0, the number 0, the rational number 0 is in 0R. Is in 1R. Is in 1R. Because 1 greater than 0. The rational number 1 is greater than the rational number 0. And 0 is not in the cut 0R. Okay. So even these proofs are kind of tedious. I'm kind of using it as the what's it called? As some kind of reminder for refreshing basic proof writing skills. Right? These are obvious statements, and some of them are not so obvious. Like, expect some difficulty when we prove M5. By the way, we encountered great difficulty. Not that great, but struggled for a little bit, like 15 minutes or so, when we were proving A5. Okay, so there's not everything is completely trivial, but a lot of these are trivial, and it's a good practice to write them in full to refresh our proof writing skills, right? Because we can't really handle hardcore analysis proof unless we know these skills well. Okay, so what does this boils down to? 0 is in 1R but is not in 0R. and 0 is a subset of R. So therefore we have proper containment. This shows that 0 R is properly contained in 1. Do you have a proper containment symbol here? Negated relation, yeah, this one. And thus, i.e., okay, i.e., because we defined less than as proper containment. So this is done. Okay, 1 is greater than 0. That's proved. And now we need to check the identity. Okay, now we need to check the identity. 1 times alpha is equal to alpha. We need to check this identity. How do we do that? We start by letting alpha to be an R plus. Be arbitrary. Let's fix that. And we need to prove that 1 times alpha is an alpha. Which direction is easier, do you think? Chat. Which direction do you think is easier? Well, 1 times alpha equals to alpha is an equality, right? So we need to prove double containment. Which one is easier? Well, why don't we start with the why don't we actually check the A4, which direction we did earlier? This proves A4, right? Yeah. Oh, actually, we need to show 1 is a cut. We need to do that. 1 is a cut, but that's very obvious. That's so obvious, so I'm going to omit that. Okay. Technically speaking, I should prove 1R is a cut. Right. 1R is not empty because it contains 0. 1R is not the whole Q because 2 is not in there. So that proves the first property. The second property, well, if P is less than Q, if P is in 1R and Q is less than Q is less than Q is less than P. If Q also less than P, then Q is less than 1, right? If P is in 1R, then P is less than 1. If Q is less than P, then Q is less than 1, so Q is in 1R. So it's exact same proof as 0R is a cut. Right. And now we need to prove that 1R has no greatest element. Well, you just pick the average, so to say, of P and 1. The average between P and 1 is always greater than P and is less than 1. That shows that 1R has no greatest element. Okay, I see a comment. For all R in 1R, R less than 1, for all S in A, we see that, which implies yeah. So exactly, you did it perfectly. Thanks a lot. You helped me out there. Okay, so the first containment is easier, right? Actually, I don't know if it's actually easier, but it's certainly not difficult to see why. Okay, great. Let's actually let me just write down your proof pretty much verbatim. You're doing my work, okay, which is great. You know, the whole reason I started this live streaming business is, I mean, it's not a business yet, okay. This whole live stream activity is to well, you know, doing math is a solitary work, and sometimes it takes a toll on you, right? So why don't we just do it together? So anyway, here let's prove the first containment. Okay. We need to show we first show that 1 alpha is not in, but a subset of alpha. Okay, so let P in 1 alpha, which is element, right? So that means then P is less than And copy the sentence we've used a bunch of time already. And P is less than or equal to R times S for some R in 1 R. Okay. I'm following your instruction. And S is in alpha with R and S positive. So that's it. So that's basically the implication here. Well, and now, because R is in 1R, since R is in 1R, it is less than 1. Okay, therefore, thus you have P times P is less than or equal to is less than, actually strictly less than 1 times S, which is equal to S. So S comes from alpha and P is less than S. By the property of cut, everything to the left of S is in alpha. This proves P is in alpha. So this completes the element chasing. And the first direction is now, first containment is now proven. Right? So now we need to do the other direction. We let P is in alpha. We need to show that P is bounded by a product, R times S, where R comes from 1 and S comes from alpha. So how do we do that? Well, if R comes from alpha, then R must be less than 1, right? So how do we find an element in alpha that is greater than P? We need to do some scratch work, I think. So this is the situation for the reverse direction. Okay, so this is a positive cut, say alpha. And here, and this is another cut, which is 1. Okay, this is 1. So we wanted R, okay, P is an arbitrary element in alpha. So we wanted an element R is less than 1. This is R. We want R. We need R in 1. And S in alpha such that R times S is therefore there exists an R such that therefore S is in 1A. There exists an R such that R. We need R times S to be what? To be greater or equal to P, right? Okay, let me just put down the first paragraph or sentence of the proof. We then show the reverse direction. This is a reverse element chasing. Let P to be in alpha. We need to show there is something in 1 and something in S, such that P times. I can't just pick S to be P, right? Even though P here is less than or equal to R times S, I can't just let S to be P because R otherwise is 1, but 1 is not in 1 alpha. Does my previous comment make sense? Okay, I didn't finish reading. I was let me take a look. For all S in A, or all S in alpha, I think that's what you mean, there exists an R such that R is greater than S. That's totally correct, because alpha has no greatest element. That is correct. So you just, okay, so this is actually a great idea. This is perfect. This is perfect. Thank you so much, man. You nailed it. Let P is in alpha. You're absolutely right. Alpha has no greatest element, since alpha has no greatest element. Yeah. Okay. Yes, your comment absolutely makes sense. If alpha has no greatest element, then there exists R greater than P, and R is still, there exists R in alpha with alpha greater than P. Okay. So now you need to take the reciprocal of R, right? R, and actually, you know what? We can, without loss of generality, assume P is positive, right? We can do that. So let's just assume, because if alpha is negative, once again, if P is negative or less than or equal to 0, it's automatically in 1 times alpha. So they just if P is less than or equal to 0, then P is in 1 times alpha. That should actually come after this sentence here. Okay, so we assume P is greater than 0, and then continue. Since alpha has no greatest element, there exists R in alpha that is greater than alpha. That is, there's R in alpha which is R greater than P. Okay. So since P is positive, then since P is positive, then R is positive. R is positive, and therefore 1 over R is 1 over R. I need 1 over R to be less than 1, right? I need 1 over R to be less than 1, but the thing is 1 over R might not be less than 1. I'm reading your second last comment. If S is less than R, if S is less than R, then S equals to R times Q, where Q is less than 1. I don't think you need that now. I need something in 1, right? I need to show alpha is contained in 1 times alpha. I let P is in alpha. Okay. And now that I have this, I have this thing, R is in alpha. I still need something come from 1, so that the product of these two bound P. I need something that is less than 1. That's the thing. Actually, I started working on that when I started saying, okay, how do I pick something that's slightly less than 1, and then I get a product, and I get something that is greater than P, right? Greater than P, so that these two multiplying together is greater than P. That was what I was trying to say. Actually, you know what? Let me refer to, hang on, there's a question. Q is in 1R, in that comma. Q is in 1R. So Q is in 1R. If Q is in 1R, then what? Q is in 1R, so Q is less than 1, right? You said Q is in 1R, then that means Q is less than 1. So P is less than R. And so you see, that's the problem. We have P is less than R. That's certainly okay. And Q is less than 1. So Q is in 1R. R is in alpha. But we need P to be less than R times Q, and that's not guaranteed. You have P times Q is less than R, but not P less than R times Q. Right? If you just pick an arbitrary Q in 1R, it might not necessarily have this relation we want. I was thinking actually, because here we allow equal sign, right? I was thinking that if I pick an R in alpha, this is our R, and then I'm going to pick just 1 over R. But the thing is, 1 over R does not necessarily less than 1. That's the problem, because R might not be greater than 1, right? So I was thinking, oh, 1 over R is less than 1. So 1 over R times R immediately gives what we wanted. Oh, actually, you know what? That was silly. That was silly me. That was not that difficult. So I could just let P over R. That's in 1, right? R is greater than P, greater than 0. So P over R is less than 1. So P is less than or equal to R times P times R, QED. Right? So really, yeah. Basically, it's still your idea. I was just how doesn't that comment prove it? Yeah. So I'm just I was stupid. Okay, sorry. So here this we then show. Let's start over. We then show that 1 alpha contains alpha. Yeah, that works exactly. That works. That P is an alpha. If P is negative or not, if P is non-positive, then P is in 1 alpha automatically. So we assume P is positive. Since alpha has no greatest element, there exists R in alpha with R greater than P. So yeah, my brain short-circuited. All right. So that was so therefore, since P is greater than 0, R is greater than 0, and here comes the thing we just figured out, that I just figured out, so that P over R, right? So P over R is less than 1, right? So P over R is less than 1. So P over R, and therefore P over R. So P over R is in the set 1R. Okay. So together, since P is less than or actually equal to, so less than or equal to still works. P is less than or equal to something that comes from 1, which is P over R, and then times R, right? So this part comes from 1, this part comes from 1R, and this part comes from alpha. So we're done. P is in 1 times R, 1 times alpha. So this completes the reverse containment. Yeah, this proves the other direction. Perfect. Excellent. Thanks a lot. All right. So this is the proposition 4. Okay, this is proposition 4. Let's go with proposition 5. I think I can delete this now. Okay, awesome. So now, next proposition. Actually, let me put an underscore here, just to, it's just easier for me to see which part is which. Okay, the last proposition says, oh well, we have this inverse. Okay, how do we prove the reciprocal exists? Well, so first we need to define the reciprocal. How do we define the reciprocal? If we go back to how we defined our additive inverse, this was how it was done. So here we have the 0 here, and alpha is here. So alpha, we want to define negative alpha. So negative alpha is our candidate for negative alpha, which is called beta. The way we define beta is that it's a collection of points P such that its own negation is not in alpha. But it turns out it's not quite enough, because alpha does not include its boundary point, so to say. So we don't allow minus P to sit right at the boundary. So therefore, we instead says minus P minus R. Minus P minus R is not in alpha for some R positive. So that is to say, minus P sits strictly to the right of alpha, if that makes sense. There's some gap between minus P and alpha. That was the definition of the additive inverse. So can we use this idea to define a multiplicative inverse? So let's see. Okay, so it will probably be helpful if we draw a diagram. All right. So this is our positive cut. Right. This is our positive cut, 0, and this is our alpha. So 1 over alpha must be positive. Right. We want it to be positive. This is a design choice. Okay. This is 1 over alpha. So here I'm obviously assuming alpha is greater than 1, but it doesn't have to, I think. So what is 1 over alpha? So we want 1 over alpha to consist of the set. In this case, alpha is an element. In this case, A is an element, not a set, right? I mean, alpha is a set. It's a cut. I want to define the reciprocal of a positive cut. That's the idea. Okay. So 1 over alpha is a set. P consists of P such that 1 over P is not in alpha, and that's not quite enough. 1 over P needs to be strictly to the right of alpha. That makes sense. 1 over P. 1 over P. I don't want to introduce subtraction here. I don't really want to introduce subtraction here. But basically, if I shrink this a little bit, okay, if I multiply 1 over P times R, so to say, this is still not in alpha. For some R positive, but is less than 1, if that makes sense. So I want to define 1 over alpha to be this way. Right? So that makes sense? Because the idea is I want it 1 over alpha to consist of numbers as such. 1 over P is in R plus, but not in A. Yes. Yes. I think I need to add the negatives too, right? I think I need to add the negatives manually. So the idea of this sentence is, when you take the reciprocal of P, it should fall out of alpha. But that's not enough, because alpha does not contain its maximum, right? And alpha does not contain its maximum, and we don't want 1 over p to sit right at the boundary of alpha. So that's why we introduce this shrinking factor r. So we want, basically it says 1 over p is not in alpha and is not on the boundary of alpha either. So there is a little gap, at least a little gap, some kind of wiggle room between 1 over p and the boundary of alpha. So we allow 1 over p to be shrunk by a factor of r. Here r is a number less than 1, and this is still not in alpha. Okay, so that's the idea, and we still want the negatives as well, right? So this, if you have if p is negative, right? Here alpha is in r plus. If p is negative, then 1 over p would still be in r. So this obviously refers to p that are positive with this property, and union the then and union what's that? And then union p such that p is less than or equal to 0. I mean, it's not that elegant, but it works, right? Wouldn't the gap exist anyway, since A is not closed? Okay, so let me just give you a concrete example. So if, let's say, this is 2, okay, this is the cut for 2. So how do we define a 1/2? The cut 1/2. This is 1/2, right? This is 1/2. So if I simply define the cut 1/2, okay, r, to be pedantic, as p greater than 0, let's focus on the part greater than 0, okay, such that 1 over p is not in 2, union the negatives, the non-positives. That means 1 over p can still be 2. 2 is not included in the boundary. Okay? 2 is not in the cut 2. So simply requiring 1 over p to be not in 2 allows 1 over p to be 2, which means I allow p to be 1/2, and this is not what I wanted. You got that? It's quite subtle. So basically, I want 1 over p to be not in 2, and that's not enough. I still want some kind of gap between the number 2 and 1 over p. So that's why I allow 1 over p to be shrunk by a little bit. Okay, so this is kind of subtle. Anyway, so this is our definition for 1 over alpha. Okay, so this is our definition of 1 over alpha, and I think this will work. And we need to prove, first of all, it's a cut, right? First of all, it is a cut, and then it also satisfies this identity. Okay, so you see, a lot of work. This is very infuriating, let's be honest here. So that's why I guess most courses don't really cover that. They just sort of hand wave over it. So, but we have all the time in the world to do this. So define 1 over alpha to be the set, of p greater than 0, such that, you believe that? My cat is sitting on my right arm, so I can't type. My goodness. 1 over p times a shrinking factor called r is not in alpha for some, there exists r I'm not sure if you can hear a cat purring from the audio, but that's literally what's happening right now. Okay, I should have a webcam at some point Anyway, so this is the most essential part, and then taking the union of p that are less than or equal to 0, p such that the negatives. All right. Okay, so this is 1 over alpha, the reciprocal. Well, we need to check that this is a cut, and then we verify the identity. Okay, you faintly can't. That's the thing. She's very heavy. She's sitting on my right arm, so it's very awkward for me to type, and I don't want to, she's happy. I don't want to push her away. Anyway, so we need to show actually, let's just show 1 over r is in r plus. My goodness. And she's so cute. Anyway, and we need to show this identity here. Okay. And here, this is, I think, a little bit confusing, because 1 over alpha, this is considered a whole symbol, okay? And the 1 on the right-hand side is the 1r. So this might be a little bit awkward. But we'll always keep that in mind. Because as far as our definition is concerned, there is no subtraction, there's no division yet, right? There's no division, basically, because there is no, if we have not defined multiplicative inverse, then there's no division. So 1 over alpha is treated as a single entity, not some kind of operation. Okay. All right. So how is this a cut? Well, first of all, it contains all the negatives, right? It contains all the non-positives. So we just need to show that the 3 things that defines a cut. Right? So the 3 things that defines a cut. First of all, it is not empty. It contains all the so let's start with 1 over alpha is not empty, and it's not the whole Q. Fun fact, I don't think there is a single analysis book on the market that mentions Dedekind's cut who does not leave most of these proofs as exercises. Okay. Not equal? Is that how you type that? Not equal. Not equal. Yeah. Empty set. Or the set Q. All right. So what's so the non-empty part is easy. Since 0 is in 1 over alpha, 1 over alpha is non-empty. Goodness, it's so difficult to type. Can you please move? I'm sorry. Okay. Okay. I have to persuade her to leave. Would P be in your definition? Would P be in alpha in your definition of 1 over? This way is easy. It will be easier to prove that. Would P be in A? What does that mean? So P is just a generic element in 1 over alpha, right? So P is 1 over A is you can't just have P positive, right? Because it's a cut. So it needs to contains everything to the left. You can't just pick the positive part, even though that's the most essential one. Right. I don't think that this will give us too much problem. Okay, so all right, so this is not empty. To show that it's not the whole Q, how do you prove that it's not the whole Q? Well, if we pick, let's say, I want something that is not in. Okay, so I think I might need to do a case. So basically, I wanted to show that based on this definition, I need a claim. So basically, if alpha is 1, then 1 over alpha is 1. If alpha is greater than 1, then 1 over alpha is less than 1. You get it, right? So that's the obvious property. So the claim is that if alpha is 1, right? So this way I can find something that is not in 1 over alpha. Then actually, to do that, we first need to show it's a cut. Otherwise, comparison does not make sense. This comes later, I guess. So why is not the whole Q? Why is it not the whole Q? Can we see how we did the addition part? Addition. Okay. Here, here's how we define the minus. Need to show that this is not the whole Q, so I take any Q in alpha. We claim that minus Q is not in. Okay. Square root of 2 is not in 1R. Therefore, 1 over 1R is not Q. No. So square root of 2 is a cut, right? Square root of 2 is a cut. So I wanted to show a cut is not equal to the whole set of rationals. It's not that it's not in Q. Okay. So I think I'll follow this. How we did the proposition 5 or A5. So if let's say P is in alpha, if P is in alpha, then 1 over P must not be in 1 over alpha, right? So here we have a shrinkage factor, R. So without a shrinkage factor, it should be further away from 1 over alpha, right? So that's the idea. So if P is in alpha, if P is in, how do I do the, my apologies, I'm getting a little bit tired. So if Q is in alpha, then we claim that this is not in beta. If this is not in beta, then show beta is not the whole. Okay. I'm using the case where A is equal to 1R to show that 1 over A is not Q. I show, that's the idea behind that comment. Okay. Using the case where A is equal to 1R and show that 1 over A is not Q. A is equal to 1R. Here we need to show this is never 1R, right? So we don't want to show that 1 over alpha is not Q. For some alpha, we want to show this is never Q, basically. So this has to be a generic alpha. All right. So basically, let me just do that. If P is in alpha, we claim 1 over P is not in 1 over P is not in 1 over alpha. If that claim is shown, then it shows that 1 over alpha is not the whole Q. So how do we show that? Well, 1 over P, so P is in alpha, like let's say P is here. 1 over P, 1 over P is not in alpha. Suppose for a contradiction that it is in alpha, it is in 1 over alpha, or a contradiction that 1 over P is in alpha. Suppose this is true. Okay, then we have, then by the definition, we have R over P not in alpha for some R less than 1, greater than 0, less than 1, right? So 1 over, oh actually, 1 over P is in 1 over alpha. That means R over 1 over P. R over 1 over P, that's R times P. Then RP is not in alpha. And that's a contradiction because RP is less than P. Everything to the left of P. Do you think the book has aged well? Does I just compare it to something like Tau? If you are learning analysis for the first time, do not use Whittaker and Watson. Okay? There is no other way to say it, unless you have a very good teacher like me. Sorry about that. Okay, that's not what I mean. Okay, I'm just saying that if you're learning analysis for the first time, Whittaker and Watson is not an ideal choice because the language is antiquated. And what I'm doing here is I'm trying to recast everything into modern notations. Okay, but that does not mean old books are useless, because Whittaker and Watson to this day is still one of the highest cited books on analysis, especially in the field of, for example, asymptotic expansions and linear differential equations or integral equations. That comes in the later part of the book. And also, it's especially so, complex analysis and special functions. Okay, but if you're learning, say, analysis, Tau would be. I never read Tau's book. Okay, let me just be honest. Analysis books are hard to read. Let's be honest. I read what? I read. There is a book called Understanding Analysis by Stephen Abbott. Okay, that was my introductory text to analysis. And actually at the same time, while I was doing that, I used Baby Rudin as a reference. As a reference together to study analysis. And now, I couldn't use these books for live stream because that's they're copyrighted material, right? So I don't want to get channel demonetized. But at the same time, I do want it to go back and use the classic text, okay? Because I know some analysis, I can translate those, so to say, more or less antiquated language into modern notation. But the language and the insights are not the same, right? You know, Newton's Principia is considered antiquated, but still, there's some brilliant arguments in there. right? So basically, what we're doing today, I only showed the time we spend on the text per se is like one sentence, because the text only define, okay, this is what it means to multiply two cuts. You can easily verify X, Y, Z. And that's what we're doing. Okay, so imagine that, telling that to a beginner. I don't think that's very fair, right? But anyway, so I hope I answered that question. So it all depends on your objective and your time constraints, so to say. Anyway, so here, let's finish up this proof by contradiction. So here, because P is an alpha, since P is an alpha, then this is a contradiction. Alpha, since P is an alpha, and R times P is less than, and R times P is less than P. This is a contradiction. Do you upload these notes? Yes. Actually, I'm working on it. I'll create a GitHub repository and upload all the stream notes. Yes, I will. Hopefully very soon, sometimes this week. This is a contradiction. I absolutely will. Anyway, so this is a contradiction, so therefore the set, the cut 1 over alpha, is not the whole Q. Okay, I've been a terrible salesman for Whittaker and Watson, I know. But I don't want it to mislead people, you know. So yeah, reading classics is inherently difficult, right? First of all, they are meant to be read like multiple times, and also the prerequisites are different. The prerequisites back then, back in the early 20th century, is very different, and the culture is different. This Whittaker and Watson, most of the exercises from Whittaker and Watson were taken from so-called Cambridge triples. The exercises are insane for the most part. So if you let's say judge your own ability based on those exercises, you can easily give up, right? But that's the point, right? We wanted to see what limit we can push ourselves to. Okay. Okay, and this is our first property of the cut. And the second, we need to show everything to the left of an element in the cut is still in the same cut. So if P is in 1 over alpha and Q is less than P, and Q is less than P, we want to show that Q is also in 1 over alpha. That's the second property of the cut. So how do we do that? Well, how do we do that? So first, let's take care of the trivial case first. If Q is non-positive, then it's automatically 1 over alpha. If Q is less than or equal to 0, then Q is in 1 over alpha automatically. So we just focus on the non-trivial part. Assume Q is greater than 0. Q is greater than 0. Okay, let start by writing let P in 1 over alpha. There will be a specific repository that stores these nodes. That's for sure. P is less than, Q is less than P, but Q is positive. Okay, so we want that. We need to show that Q is in 1 over alpha. So to do so, we need to verify this property. We need to show that there is existent alpha, there exists an R, there exists an R such that R over P is not an alpha. Well, let's start with since P is in 1 over alpha. Since P is 1 over, actually, yeah, P is positive here. P is positive, so therefore we can write R over P is not an alpha for some R positive and less than 1. So that's the that comes from the assumption. So Q is less than P. How do we use that? Q is less than P. How do we use that? Well, we need to show that 1 over R, not 1 over R over some R over Q is not an alpha. That's our goal. We need to show for some R in 0 and 1 that R over Q is not an alpha. So here, well, what is the same R over Q? Since Q is less than P and its Q is positive, if you take the reciprocal, R over Q, it's got to be greater than R over P. But the thing is, R over P is already not in alpha. R over Q is even greater than that. It cannot be in alpha either. We have a little proposition for that. Okay? If something is not in a cut and something else is even greater, then basically that something else cannot be in the same cut. Okay, so this is not an alpha. For the same R. Okay, for the same R. So this shows that. This shows that Q is in 1 over alpha as needed. So basically that's the second property. Everything to the left of P is still in 1 over alpha. All right. And 1 over alpha, we need to show 1 over alpha has no greatest element. That is to say, if P is in 1 over alpha, P is in 1 over alpha and if P is in 1, there exists, okay, there exists Q in 1 over alpha such that P is less than Q. P is less than Q. This has no greatest element. Okay. All right. How do we do that? So first of all, if P is, say, if P is, say, non-positive, let's do the trivial case first. If P is non-positive, well, if P is non-positive, That means you can pick any positive. No. You can pick any positive in 1 over alpha. So 1 over alpha must contain positive. Right? Because 1 over alpha it has to contain positive, right? I didn't even show that. I didn't even show that it contains positive. Does it contain positive? Well, let's just say we want to show that there is something positive in 1 over alpha. I think it would be a good opportunity for a contradiction, no? Let's say, because 1 over alpha is at least p less than or equal to 0. Let's suppose everything, there's no positive. If we assume that there is no positive, that means what? If 1 over alpha has no positive in there, look at the picture. If 1 over alpha has no positive in there, and we can get a contradiction, then alpha is equal to r. You mean alpha is equal to q? Let's try to prove that, okay? If 1 over alpha is just p such that p is less than or equal to 0, okay? That's the only way it would have no positive. If we define that, then what happens to the reciprocals in there? What happened to the reciprocals in there? So let's say 1 over p would be negative, right? 1 over p would be negative. But 1 over p would, if 1 over p is negative, then it's in alpha. Is that a contradiction? Is that a contradiction? So how do we, a contradiction of what? So it contains 0. We know that it contains 0. Why it must contain positive then? If it contains no positive, then what time is it now? It's 9:12. I can't stay for another 18 minutes. I'll stay until 9:30. So it looks like you can't finish, but it's okay. I was planning to finish the Dedekind's cut today, but it's all right. Things happens. So, well, if I need to show it has a positive at least. You said alpha is r. I suppose you mean alpha is the whole Q, right? But alpha is not whole Q. 1 over alpha is not the whole Q. So if let's say, okay, I want to pick something that is positive. How do we construct something positive in there? By R, I mean the real number set. Well, the set of real numbers, by the way, is the collection of all cuts, by the way, and that's our definition. The set of all real numbers is the set of all cuts. So 1 over alpha, we want to show 1 over alpha belongs to that set. It can never equal to that set, right? So that's a category error, unless I'm okay. How do we show that there is something positive in there? Alpha is here. Alpha is here. So we need to construct an element. Yeah, so if 1 over alpha has no positive, then A must be the real number set. Well, alpha, so if 1 over alpha is equal to, is equal to minus infinity, I'm just abusing the notation, okay? I hope this is okay. Then that means the set P greater than 0 such that there exists R in 0 and 1 such that R over P is not in A, not in alpha. This is the empty set. Because 1 over alpha is the union of those two, of this and this. This is the empty set. So that means there's no P greater than 0 that has this property. There's no P greater than 0 that has this property. That means for every P greater than 0, this property fails. What does it mean by this property fail? Well, this property fail, we negate the statement. That means for every R greater than 0 and less than 1, R over P is in alpha. R over P is in alpha. For every, that's the negation of this statement. R over P is in alpha. Every P greater than 0, R over P is in alpha. So R is something is less greater than 0, less than 1. 1 over P is 1 over. For every P greater than 0, it has this property, 1 over. So we only get the negatives if alpha is a real number set. So that means essentially the alpha is unbounded, right? That's the idea, because P is greater than 0. P is greater than 0. R over P can be arbitrarily large. It can be arbitrarily large, which is a contradiction. That's not possible. That would be unbounded, right? So that's I think you're right. I think you're right. It's just that the phrasing is a little bit weird. I'll heart your comment. Can we do that? Can we? How do I do that? Okay, this is the insight is, even though the language isn't completely correct, but the insight is correct. I think what you're saying is, if this is empty, because at this point there's not even the set of real numbers. Okay, the set of real numbers is something we talk about after we establish the existence of a complete ordered field. Okay, so now we have the set of cuts, which is still to be constructed. Okay, the set of cuts that is to be verified, that satisfies the definition of a complete ordered field. So anyway, I'm getting too far. So basically, I'll just write down the proof that you just mentioned. So here we first show that there is something positive. We first show that there is something positive. There is a positive rational, a positive. There exists P positive, that is such that P is in a set 1 over alpha. Okay, it always has something positive. Let's suppose for a contradiction that it isn't. Oh, if the set of real numbers isn't defined, why do we have R plus? Okay, so by that, the set R denotes the set of all cuts. This is a prototype for the set of real numbers, because the collection R of all cuts, this is cut. We haven't advertised that this is the set of real numbers yet. Okay, we wanted to prove this has all the properties of real numbers that we wanted. Okay, so as far as the symbol is concerned, this is the set of all cuts. Everything in there, okay, is a set, is a cut, right? A cut is a set of rationals. So that's why I was avoiding the phrase real numbers at all time, right? Because I don't want to make the logical error that we already have the real numbers. The real numbers is a complete ordered field, which can have many constructions. Dedekind cut is one of them, right? And now we wish to show that Dedekind's cut has all the desired properties we have in mind for the real numbers, right? So that's how we define R, the set of cuts. The cut is a subset of Q, which is these properties. This is a cut, and the set of all the cuts is called R. Right? We haven't used the R word yet. Okay, we haven't used the real number word yet. Right? Okay, okay. So that's the mental gymnastic we're playing. Okay. Thanks for sticking along for so long, by the way, man. Thank you so much. This is incredible. Imagine watching somebody doing dry math while you can see somebody else playing video games or something else. This is incredible stuff. I cannot believe it. But anyway, there you go. This is R plus. This is the set of all positive cuts. So there you go. Anyway, so let's just, I see what you mean. I see what you mean. That was a brilliant argument, and I will reconstruct it here. First, we show that there is something positive. Suppose for a contradiction that there is none. That 1 over alpha has no positive. Okay, so by our definition, this is our definition of 1 over alpha. That means the first part is the empty set. This would mean this is the empty set. That is, for every p greater than 0, this property is fail. This property fails. The property fails, right? Otherwise, it cannot be the empty set. So that means that we just keep translating. For every p greater than 0, for every p greater than 0, R over p is in alpha. You need to negate it for every when you negate a quantified statement, you flip the quantifiers from there exists to for all, and vice versa. And then you negate the condition itself. The thing is, here p is arbitrarily So let me just pick. So therefore, let me just pick 1/2 p. Let's pick. This is true for all r in 0 and 1, right? I can just pick r equals to 1/2. So 1 over 2p is in alpha. Is in alpha for every p. But this is unbounded. So this is unbounded, so alpha is the whole Q. Because 1 over 2p can be as large as possible. Can be arbitrarily large. And thus Q. A contradiction, because alpha is a cut. Right. Okay. So yeah. So that's it. So this is, there exists something positive. So after we have that, so this is, we can say, thus, if p is less than or equal to 0, oh, that's good. Okay, yeah, it is. It's your idea, man. If p is less than or equal to 0, if p is less than or equal to 0, then there exists Q in 1 over alpha, such that p is less than Q. Right? So that's it. That's it. So this is trivial. Because we showed that there is something positive. If p is less than or equal to 0, well, because there is something positive, so p is automatically less than that positive thing. Okay, so for that we assume that p is positive. Assume that p is positive. Right. So assume that p is positive, and now we need to show there is something that is greater than p that is still in 1 over alpha. How do we do that? So go back to the picture. This is getting way too messy, so I'm going to delete everything here and redraw the diagram. All right, so here we have what? This is p. Okay. P is in 1 over alpha. This is 1 over alpha. Okay, suppose alpha looks like this. Alpha is look like this. Okay, so P is in 1 over alpha, and we want to show that there is something greater to it. All right, so P is in 1 over alpha. This means there exists R in 0 and 1 with R over P is not in alpha. So we wish to construct a Q. Okay, wish to construct a Q. Such that Q is in 1 over alpha. So if Q is in 1 over alpha, then for some R star in 0 and 1, R star over Q cannot be in alpha. Also, P needs to be greater than Q. So imagine this is 1, okay? So imagine this is 1 and this is 0. P is here. 1 over P is here. if Q is here, then 1 over Q should be even less than 1 over P, right? So we want the shrinkage factor to be even smaller, so to say. R is the shrinkage factor for 1 over P. 1 over P is not in alpha for sure, but we want we have R over P is not in alpha either. Okay. So what do we squeeze that? 1 over alpha. 1 over R over P is not in alpha. Yeah. Let's go back to the proof for the minus and get some inspiration from there. All right, so that's this property here. So we define the minus as such, and then we say assume that P is in beta. We need to exhibit some T in beta with P less than T. Yeah, so showing that beta has no greatest. Since P is in beta, P minus P minus alpha minus R is not in alpha for some R greater than 0. Take that P plus half R. So this way P is less than T. So that's correct. P is less than T. That's correct. And then flip the minus sign. Flip the minus sign. Therefore, Q is in 1 over alpha. P is less than Q. Then R. If yeah, I get what you mean. It's a good idea. If P is less than Q, then R over P is greater than R over Q. If R over P is not in A, then R over Q cannot be in. Hang on. R over P is bigger, right? R over P is bigger. You can only say okay, if something is not in a cut, then everything that is larger than it is not in the cut. I think this is not quite right. You have R over P greater than R over Q. R over P is not in A. R over Q is to the left. It's to the left of R over P. You cannot say because it's to the left of R over P, then you cannot say it guarantees that it's not in A. No. I think it shouldn't be that hard based on how short this proof is. You just need to modify it to get the right argument for multiplication. All right. I'm getting a little bit tired. So yeah, you see, 1 R over Q. This is 1 over Q is less than 1 over P. R over Q is indeed to the left of R over P. We see that here. If this is the other way around, what happens if it's if P is here and Q is here? And 1 over Q is still to the left of 1 over P, no? 1 over Q is still to the left of 1 over P. It doesn't matter the relationship between 1 with 1. When you have time, what do you mean when you have time? Actually, I'm running out of time. I'll finish this and I'll go. Okay, but hi, thanks for joining the stream. So here we have assume p is in 1 over alpha, and p is positive, okay? P is negative is trivial. Assume that. We need to exhibit some t, need t in 1 over alpha with p is less than t. Yeah, this is what we need. Since p is in 1 over alpha, okay, since p is in 1 over alpha, 1 over p times r is not in alpha for some r greater than 0, less than 1, right? So that's just the definition. Okay, and then what happens? And then if r over p is not in A, so here let's take our t to be our t to be we need t to be greater than. Can we write, let's say, p over r squared? P over r squared is greater than p. That's guaranteed. That is guaranteed. But is t still in 1 over alpha? Well, 1 over t is what? 1 over t is r squared over p. R squared is r squared over p. But r squared is greater. But r squared is less than it. I need this to be. I need something that is greater than r. I need something that is greater than r. So I wanted to use the square root, but damn, square root may be irrational, right? The square root of r, because r is in 1 and is in 0 and 1. The square root of r would be greater than r. So this way I can cook up something that is in the set. Hang on, maybe that's. I need one over p over. What's the multiplicative counterpart of p plus 1r? YouTube deletes my message. Sorry. R over 2. Yeah. Well, what about r over 2? What about r over 2? So here we have. You want 2r over p, right? This is what we want. 2r over p. Is that too much? Is that too much? So here, because we said minus t minus half r is the same as minus p minus r. So it's essentially the same thing. So essentially we still want the end result to be 1 over p minus r. But we just wish to cook up from this, we wish to cook up something that is greater than p. Greater than p, and is hang on. Maybe do this. Half r times 2p times 2 over p. Does that work? Is this our? But the problem is this is supposed to be 1 over t, but in this case t is less than p. You know, that ain't good. So here we have minus t equals minus t minus half r. Minus t minus half r is minus p minus r, so it's not in alpha. So we want the reciprocal of t times something. Times something, that is wanted to use the square root of r if let's say if the square root of r is rational. If the square root of r is rational, let's forget about irrationality for a point, for the moment. Okay, we have r over p is not in alpha. And then we can just rewrite square root of r over p times the square root of r. The square root of r, this is still in 0 and 1. And the square root of r is actually greater than r. So this way, square root of r over p is greater than p. But now we cannot invoke the square root of r. Okay, this is an absolute mess. My goodness, that's disgusting. All right, so let me just throw this away. Okay, this is, sorry, remind me again what we're trying to prove. Okay, we absolutely need to do that because I'm on the brink of confusion as well. What we're trying to prove is as follows. Here we assume p is greater than 0. Okay, we wish to show that there exists a q that is in 1 over alpha and is greater than p. So basically, p is a positive element in 1 over alpha and p is not the greatest element. You just got here, want to see the full problem. Okay, Torresilatiano. Okay, sorry, I can't pronounce your name, but basically this is what we're trying to do here. Okay, just a quick walkthrough. So we're in the theory of Dedekind's cut for the real numbers. Okay, the idea is we wish to construct a set that satisfies all the properties of the real numbers we want. And currently we are at the stage of defining a multiplication. Okay, actually we just defined the multiplication between two cuts. We just defined the multiplication for two Dedekind's cut that are positive, and we wish to show that this definition allows us to define reciprocal. That is to say, the reciprocal is also a cut, and also it satisfies the property of reciprocal. That is to say, the reciprocal times the original cut is the cut 1. Okay, I know. If let's say you have never seen the Dedekind's cut before, this will unlikely to make much sense to you. But you can catch on to my screen summary videos to appreciate what we're doing. So we're here at the very last step of showing 1 over alpha. This definition that is our candidate reciprocal is indeed a cut. Right, so we're at the very last property. The very last property says a cut cannot have a maximum, and we're trying to show that. Okay. Okay. I hope things gets a little bit clarified. Okay. I encourage every one of you to not get discouraged, because this is the problem that that perplexed the entire mathematics over 2,000 years. Okay, so it is very natural that we struggle from time to time at this point. It is not meant to be easy, because the jump from the rational to the real is much harder than the jump from the reals to complex. Right? So after we have the real numbers, the complex numbers are very easy to find. But if we only have the rationals, to find the real is a very tricky business. It took over 2,000 years to get some sort of modern solution, even though today is still controversial. Okay? There's still people who does not accept this construction, but we as practitioners of mainstream mathematics, we do accept this construction. It's just that it's very rare that somebody works out the full details. Okay? It's usually just hand waved over. Anyway, so I was saying, so if p is in 1 over alpha, then there exists r such that r is greater than 0, less than 1, and r over p is not in alpha, right? So we need to construct a Q. Right? We need to construct a Q. We need to exhibit a Q that is also in 1 over alpha and that is greater than p. So what I was saying, I was trying to do some funny business about this r. So I was trying to rewrite this expression, which is already not in alpha, as the square root of r times the square root of r, okay, and then over p. And this is my candidate 1 over t. So basically t is equal to p over the square root of the square root of r. Obviously, this is greater than p, because r is between 0 and 1. R is between 0 and 1, and this is square root of r is once again in 0 and 1. So if the square root of r is irrational, then this completes the proof. But the problem is r is not irrational. The square root does not exist yet. Before proving the existence of a complete ordered field, square root does not exist yet in general. So this is why I'm a little bit stuck. So how do we decompose this r? Okay, so how do we decompose this r so that is there anything else we can do about it? Can we let's say we want something that is greater than r. Okay, this is r. We want something that is greater than r. So maybe let's do the quadratic function. So this is r, okay? The function of r, f of r. Let's pick the function to be above r to, let's pick 1 minus, no. So let's imagine this is a parabola, okay? With a maximum at 1, 1. So what would that be? It would be r times 2 minus r. R times 2 minus r is still between 0 and 1. That's the quadratic function. That's the quadratic function. So we want, I'm going to go now. Enjoy the stream. Thank you. When will be streaming next? I will stream every Tuesday for the moment. And when it gets to summer, I'll stream more often. Thanks very much for joining. Seriously, thank you so much. Okay, so here we have r times 2 over r. But the problem is there's no problem. There's no, this works. This actually works. Let me just say that very clearly. Since I've been wrestling with this as well. If alpha is the Dedekind that defines a real below, I've been wrestling with this as well. If alpha is the Dedekind that defines a real below 1.0 and so on, and p is in 1 over alpha, p is greater than not in alpha. Question mark? Yeah, so basically if you're saying that alpha is the set of rationals p such that p is less than 1, if p is in 1 over alpha, then p is greater than 1. That's correct. This is the correct statement. So here, okay, back to our objective. We have p in 1 over alpha. We need q such that q is in 1 over alpha and q is greater than p. Right? We need to define this q. We need to exhibit this q. So let's do that. Since p is in 1 over alpha Okay, I'll just write in the form of a chicken scratch and then we'll type it up. Okay, so P is in 1 over alpha. We already assume P is positive, by the way. P is negative is trivial. P is 1 over alpha. There exists R such that R is between 0 and 1. Okay, this is the relatively more polished proof. Such that R over P is not in alpha. Not in alpha, right? Okay. So now let's consider something. Since R is between 0 and 1, 2 minus R is greater than 1. That's my cat. 2 minus R is greater than 1. So 2 minus R, okay. Can I enlarge this? Okay, maybe I should delete something here to make space. All right. So the trick is to use 2 minus R. Since 2 minus R is greater than 1, two minus R times R over P is greater than R over P. But R over P is already not in alpha. Therefore, 2 minus R times R over P is greater, is not greater, is not in alpha. Is not in alpha. So we constructed something that is not in alpha. Well, what does that tell us? Well, what does that tell us? Well, here we have, does 2 over, god damn, 2R over P, I want this to be 1 over T. I wanted this to be 1 over T. So, my goodness. I want this to be 1 over T, but here T is equal to P over 2 minus R, and this is less than P. Or Q, okay. I wanted this to be my Q. This is so annoying, man. My God. All right, this is, okay. I failed the very last requirement. No, that works. That works. What do you mean that works? R is, I need a reciprocal, okay? I need a reciprocal times R times not necessarily R, but just something that is less than 1 to be not in alpha. I wanted to use this R, but the rest as a reciprocal would gives us Q equals to P over 2 minus R. But the P2 minus P over 2 minus R is 2 minus R is greater than 1, so this is less than P. Because how is that greater than P? 2 minus R is greater than 1. So it's dividing, let's say 1.1, so this is less than P. Yeah, this is what I'm saying. P over 2 minus R. 2 minus R is greater than 1. So this is less than P. I want it to be greater than P. Right. So this goes back to my, okay. So let's, yeah. So it goes back to my original idea. Let's say I already know that R over P. I already know that R over P is not in alpha, right? So it would be nice if I can break the R into the square root of R over P and then times the square root of R. So this is not in alpha. And the square root of alpha, square root of R is in 0 and 1. This is in 0 and 1. So P over square root of R, this is because the square root of R is in 0 and 1, this would be greater than P. So this would work. So that's the multiplicative counterpart of me writing this minus half alpha in the additive case. But here, the problem is the square root of r does not exist yet, right? Unless we define the real number, this might always exist. So here we are in this pickle, right? This would work if the square root of r is irrational. All right, unfortunately, I would have to go. This is getting a bit too late. I apologize that we couldn't finish this up, okay? But then again, this is a good learning opportunity, and there will be a reflection video coming tomorrow, and feel free to type your comment to that video, and I'll see you next time, next Tuesday. Okay. Thanks very much, everyone, for joining the stream. Bye. Good night, or have a good day wherever you are. What chapter is this in Whittaker? Okay, good question. So we're still in the chapter 1, Dedekind theory of irrational numbers. Okay, so as for our material today, I was just trying to fill up the exercises left for the reader, or the details left for the reader. We're dealing with this sentence here, the product. The product of two positive reals is defined, blah, blah, blah. Right? So as a product, your channel is great. Thank you very much. So we would like to prove that this product, the so-called product defined here, satisfy all the product properties that we wanted, right, for rational. So this is, in modern terms, a field. Right? Field consists of a set that has two operations. So that's why we need to verify these 5 axioms. Right? So that's why we were doing this. Right? So just to verify this is a valid operation of multiplication, as is understood for numbers such as the rational numbers. We want to verify this product satisfied, because he says the reader will see without difficulty how to define the product of negative. We haven't got into that part yet. We haven't even got into that part. And the quotient of two real numbers. And here's the problem. We were trying to prove the existence of the reciprocal, because quotient between two real numbers is exactly the same as x times the reciprocal of y. Right? So unless the reciprocal of y is defined, we cannot define quotient. Right? So, but he says without difficulty. Okay, which was bothering us. And further, it may be shown that real numbers may be combined in accordance to, maybe combined. Okay, combined is not modern terminology. Okay, this means multiplication and addition satisfy the associative, distributive, and commutative laws. That's what it's saying. Okay, so this is not I wouldn't call it an issue, but rather an what we call a inconvenience of most analysis book. They all leave the details to the reader. I guess for good reason. They wanted us to practice. I mean, I don't want to think these people are evil, okay, to make us suffer. But the idea is we should be able to prove these things. Otherwise, the foundation of real analysis is not really secure. So that's why this is the part we're doing. Okay. After this is done, we still there are two ordered field properties that needs to be verified, and that completes the proof of existence of the real numbers. So that's where here, and I promise, after that's done, complex number is such a piece of cake. If you already have the real numbers, defining complex number is such an easy thing in comparison. It's not even on the same magnitude. Okay. All right. And actually, Whittaker and Watson mostly deal with complex analysis. Because it was written at a time where the pinnacle of analysis is complex analysis. It was before the measure theory was a thing. It was before measure theory, the functional analysis are prominent. So this sits at the pinnacle where functional analysis was developed. So that's why it has such a high prestige, so to say, in the English language. That this is considered a museum, so to say, of classical analysis. Anyway, I have to go. Okay, thanks very much for joining the stream.